Friday, we were finishing up with this polynomial. Okay, p of x equals x to the fourth times x minus 2 cubed times x plus 1 squared. And we want to graph it. Okay, we want to graph this thing. The first thing we have to know is what the end behavior is. Okay, so this thing's end behavior is dependent on what degree this polynomial is. Okay, so if I think about this, okay, x to the fourth is obviously x to the fourth. Okay, now x minus 2 cubed, well, that's going to be x cubed minus something times x squared minus something times x plus 8. Okay, and I believe it was minus something, so like 6x, might be 6x squared and 6x. But regardless, it's going to be something x to the third plus some garbage, right? Does that make sense? This is going to be x squared plus 2x plus 1, which is ultimately x squared plus some garbage. And the reason I'm just saying plus some garbage, because I don't care what that stuff is. Because when we're talking about end behavior, the leading term is all that determines it, right? Okay? So, if I got that, I could go one more step, and I could distribute that x fourth to this stuff. So that give me x to the 7th plus a bunch of garbage, right? Yeah. And then I have x squared plus a bunch of garbage. If I were to FOIL that out, it's probably not FOIL, it's probably more terms than that. I know it's more terms than that. But if you distribute this to this, x 7th times x squared will give you x to the 9th. And then you'd have plus a bunch of garbage, right? Okay. Now, I'll actually write down for us what that garbage is. This thing turns into x to the 9th minus 4x to the 8th. You don't need to write this down, but I'm just trying to prove a point to you. Plus x to the 7th plus 10x to the 6th minus 4x to the 5th minus 8x to the 4th. Okay? That is what this p of x really is. Is that okay with everybody? Yeah. Okay? And the reason I say that is, one, we need to know the end behavior. We need to know it's x to the 9th. And that validates what we came up with down at the bottom. But the second reason I say that is because later on this week, early next week, dude on the roof.
What? There's one on the roof?
A dude. It was me. I'm sorry.
Safety.
I'm kidding. It wasn't me. So later this week, early next week, we're going to start with this. We're going to start with this, and we're going to ask the same exact question this problem's asking. Graph it. Okay. So what do we need to be able to do with that to get to this? We need to be able to factor. Okay. So.
Pardon the interruption, but if you drive a silver Mustang, license plate number HWH8866, could you please come to the office at this time? Thank you.
I heard Mustang and she got worried.
All right, so we'll need to factor that. We'll need to get that down to x to the 4th times x minus 2 cubed times x plus 1 squared. Anybody know how to do that? Yep. You should all say, yes, I know how to do that.
Yes, yeah.
How?
Take out x to the 4th.
Well, how'd you know x to, okay, so you GCF of x to the 4th, and that would leave you with something like x to the 5th. How do you factor something x to the 5th? You should all say, I know how to do that.
Then you group it.
Natural root theorem, P over Q. Remember doing that last year?
Nope.
Yes, you do.
I mean, okay, we did that. I don't remember how to do
so
that.
So that's what we'll do. We'll relearn that later this week. Okay. But that will get us down to this. Now, the reason we're doing that is because these are going to be intermediate steps for something in calculus. Okay. So this might be something that in a calculus problem, we start going through it, and just the math shows up. The implied directions will tell you need to factor using P over Q so that you can get that down this P of x to be x to the 4th, x minus 2 cubed, x plus 1 squared. Okay. So that's kind of where this stuff is leading to. Right now, because we don't know how to factor those things, or maybe our skills are not as strong as they should be in factoring these, they will start us off most of the time like this, okay, right now. So let's talk about what that means to us. Let's talk about what these answers here, well, not answers, but I don't want that to happen. All right, so what does x to the fourth really mean? What's x minus 2 cubed really mean? And then x plus 1 squared. Count these. How many you got?
4, 5, 6, 7, 8, 9. You did not.
Okay. So, and that's something we'll talk about later this week, but we'll use it a little bit again today. But when I have a ninth degree polynomial, I'm going to have 9 factors. Now, they might be redundant. Okay, x equals 0 shows up 4 times, right? X equals 2 shows up 3 times. Those are redundant. But total, counting multiplicities, I have 9 zeros. Okay? Now, we need to be able to understand, well, what does this mean? Okay, well, when I solve this one for 0, that says x equals 0, but it showed up 4 times, right? So I'm going to write multiplicity of 4. This one here gives me x equals 2, but it showed up how many times? 3. And this one gave me a multiplicity of 2.
You said 2, but negative 1.
Or the 0 is negative 1, but the multiplicity is 2. Okay, so what I need to understand then, graphically, when I have an even multiplicity, my graph is going to be, it should be tangent, it won't draw down there for some reason. There we go. My graph is going to be tangent at that 0. Does that make sense? Okay. If I've got, now obviously I didn't draw the right 0, but I don't care. On odd multiplicity, my graph is going to do something like that at that 0. And then here it's an even multiplicity again, so it's going to come back up this one. Okay. Now the difference between the higher levels of even multiplicities, like a 2 compared to a 4, or a 4 compared to a 6 in regards to multiplicities, is that the higher the degree, the more that thing kind of bottoms out. It looks more like a cup at the bottom. Does that make sense? Okay. A second degree looks very parabolic when it touches that 0. Okay. So we want to come over and we're going to graph this. Okay, and get a good idea of what this graph looks like. Okay, so trying to rewrite what P of X was. P of X was x to the fourth. What I have, plus 2. Is that what it was? Minus 2. Minus 2 cubed, and then x plus 1 squared. Okay, so I'm going to find my zeros. Okay, so that was a 0 of 0. Okay, if that's my x-intercept, is that also my y-intercept? Okay, so that, probably that we said the other day, we wanted to graph these things. We need y-intercepts. This is one of those situations where knowing that, now I don't even have to look for a y-intercept because I know it's 0, 0. Okay, 2. And then negative 1, right? Okay. Now, I'm going to write on my graph just real quick what these multiplicities were. So I'm going to say multiplicity of 4. This had a multiplicity of 3. And this one had a multiplicity of 2. This was x to the 9th, right? Well, if it's x to the 9th, what's the end behavior of x to the 9th look like? As x goes to infinity, where's y going? Infinity. End behavior should look like that. Okay? As x is going to negative thing, how do I remember this stuff? What's a negative times a negative 9 times? A negative times a negative 9 times is going to give me a negative, right?
Yeah.
A positive times a positive 9 times is going to give me a positive, right?
Yeah.
And as it gets a big positive, it's going to be bigger positive in the y direction. So just knowing how multiplying positive numbers or negative numbers an even or odd number of times. Okay, now we want to look at these. We got multiplicity of 2, and I need to, and a lot of our properties I want to see here later on are because of how the end behavior needs to be maintained. If I look at that first 0 there, -1, the multiplicity of 2, right? So you got options. Multiplicity of 2 means it's either going to look like that or it's going to look like that. Does that make sense? One of those two things. Which one's it got to be?
Top one.
Why can it not be the top one?
Because it's concave.
What do I have to mind? What did we just talk about? We talked about the end behavior, right? If this black one is going to be what happens here, then this is going to have to turn one more time, right?
Yep.
And if it turns one more time to do its end behavior, what's it going to have again? Another x-intercept. Do I have any more x-intercepts to the left of that one? No. So it can't be the black one. It's got to be the red one now, right? That make sense? Okay, now, as we work through these, and we talk about this on Friday, there's going to be some issues with the size of our graphs in regards to the y-axis because we don't have calculus yet. Okay? But continuing on, first of all, I've got the behavior that should happen here to the left of this 0 and now to the right of it. Now, if I'm going down, okay, don't I eventually need to turn back up to get to this x-intercept here? Okay. So I'm going to turn back up. And it's a 4th degree, so like it's going to be more, I don't know, kind of flat there. I'm not going to really, I'll have you grab some of these. I'm not going to be a stickler on your y-axis and how, some people, some people will go up to it and bump it like that. Okay, it should be a little bit flatter there. Don't really care right now, though. Okay. So then I keep going down, but I need to get up to this thing, right? I need to get back up to that x-axis. So then it's got to turn somewhere, right?
Do you make it dotted line or should we?
Well, I'm going to make it dotted just to kind of prove a point here in a minute. If it's to the third, or the 0 was to the third right there, right? It does not just pass through straight. If it passes through straight, that would tell me it's to the first power. The third power, to the right of it's going to look like that. To the left of it's going to do something like that. Okay? We've talked about how it kind of looks like, if you look at that, sideways, tilt your head to the side, kind of looks like an S, right? Or an inverted S, backwards S.
Yeah.
That's the behavior that happens at an odd degree that's bigger than 1. Okay? Now, the reason I made that dotted, and I should have made some other parts here dotted as well, let me just highlight them. That stuff, guys, and that stuff right there. And to be honest, even these y values, I know where they're going, but I don't know how fast they get there. Those y values are undetermined right now because I don't know what my scale should be. Okay? Because I don't know what this minimum here is. Okay? Now, I can do this type of thing. We did this last period. If I put 1 in to my polynomial, so see what P of 1 is, I could have 1 to the 4th. 1 minus 2 gives me -1 cubed. And it's going to give me 2 squared, which is going to be 4, right? Negative 1 times 4. This gives me negative 4, right?
Yeah.
So I can evaluate, so I'm basically doing a table here, right? Choose an x value, figure out what p of x is. So at 1, I get negative 4. Maybe I come over here and I say, okay, well, let's take negative 1/2. Negative 1/2 in here, so that's going to be kind of ugly, but it'll be negative 1/2 to the 4th. Negative 5/2 to the 3rd. And then 1/2 squared. If you type that stuff in, negative 0.244 would be that y value. Does that make sense? Okay. Now, would you agree that creating that table there is kind of tedious?
Yes.
Okay, it's kind of a pain in the butt, time consuming, and better yet, or even more, it's not very accurate. Meaning, I don't know, I chose 1, but I don't know if that's really providing the minimum there. Maybe 1.2 provides the minimum. Okay, I don't know. Remember, and this is the thing that we've always talked about with graphing new things. I don't know when creating a table which x's to use. Okay, and it's kind of a game of guess and check, or doing multiple between 0 and 2. Maybe I do 5 or 6 points in there. Between 0 and negative 1, I do 4 or 5 points in there. Does that make sense? And that's a pain in the butt. I don't want you to have to do that. But if you wanted a more precise graph, okay, more accurate graph, that's what you would need to do right now. Okay. When we get to calculus, guys, there will be a tool that provides that minimum, that maximum, almost instantaneously. Okay? And I want to kind of demonstrate that real quick. Because it should hopefully open your eyes to what we need to learn here. Okay? So if I've got this function, I'm just going to go, GeoGebra's got a computer algebra solving system, so it's kind of nice. Let's just clear all this stuff out. How do I clear it? All right, so our polynomial started as x to the 4th times x minus 2 cubed times x plus 1 squared. Okay? Now, what a computer algebra solving system does, guys, if you know the commands, you can say expand this thing, and it will FOIL all it out for you. Okay?
Wait, was it GeoGebra?
Yes. So the thing that I want to do, and I could have done it before I expanded or not, but does that verify what we wrote down earlier where we started the problem? Okay. In calculus, you'll learn to take the derivative. And we've already done one of these. Okay. You guys remember the process of taking like this 9 and multiplying it by the number out front and subtracting 1 from it?
Yeah.
So I got 9x to the 8. Taking this number here, multiplying by the number out front, so it's going to be negative 32, and then x to the 7th. So when I ask for the derivative of this, it should give me that. Does that make sense? Okay. Remember, the derivative was showing us the slope of anywhere on that curve that we just drew, that graph that we just drew. That will give me the slope anywhere on it. Well, maximums and minimums, the slope of the tangent line at maximums and minimums was 0, right? So what we do is we take this thing here, set it equal to 0. Anyone want to guess on how you're going to solve that equation? Factor. Very good answer. And it's going to be the exact same factoring that we learn in the next couple days. First thing you do is factor GCF of x cubed out, right? And then I'll break that down to an x to the 5th. And then you'll use the P over Q rational root theorem that you guys have some exposure to continue working through that process in calculus. Okay? It's the only way you're going to be able to do it. Okay? So then, I can actually ask this thing to solve this for x. Give me some solutions here. Now, what this does, these solutions tell me where I have maximum minimums. Okay, let's go back to our graph real quick. Did we have a maximum at -1? Did -1 show up as an answer right here? It did. Did I have a maximum at 0? Right there, right? Okay. Do I have so at 2, x equals 2, it gives me, this is something that you'll learn in calculus. That test actually gives you, they're called critical points. They're maximums, minimums, or what we call inflection points. Okay. At 2, we have an inflection point. Okay. Just kind of means that we've changed concavity there at 2. Okay. Don't really worry about that right now. But these other values, okay, let's keep pushing the wrong button here. Let's look at what this number here is real quick. Let's go. And I don't know why GeoGebra does this to me, but I can't figure out. It won't let me evaluate that number. So I have to do it on my calculator. So 3, 13. Plus 5. I divide that by 18. Gives me negative 7.05. Negative 0.705. I want to do the other one. So plus 5. So 313. Divided by 18. Gives me 1.26. 1.26. Remember that number. This here is 1.26. Okay? Now the reason for that, okay, if I want to, I'm going to take this thing here, and I'm going to go to the algebra, and I'm going to graph it. Hopefully that showed up. There we go. That's the graph we just came up with. Okay? When we evaluated in our table, we found 1 comma f of 1, which would have been that 4 point right there, right? Negative 4. You guys remember doing that in the?
Yeah.
Okay. Was that the actual minimum? No. The actual minimum is right there. Okay. If I asked GeoGebra to actually find that minimum, and let me just do this. I'll just go. It was negative square root of 313. Actually, it was positive square root of 313 plus 5 divided by 18. So it was that amount, comma, f of that amount. See if this works. There we go. Close it off. See that it showed up this point B here? Give me that 1.26 number. Okay. So, in getting those specific, exact maximums, minimums, we have to be able to use calculus. Okay. But my hope is that you realize we're almost there. We're like a week's worth of calculus information, being able to do derivatives, which is just in this type of function, is just multiplying and adding. Okay. Multiplying and subtracting, actually. And then using everything that we've talked about so far in regards to factoring in college algebra. Okay. My hope is, and I know that because I've been working with some of my previous students that are in calculus right now, they're doing this kind of stuff. They're using what's called the first derivative test, the second derivative test, to figure out where these maximum, minimums, and inflection points occur. And they're getting to the point where they have to rely on their college algebra, and they're forgetting how to factor things. Okay? So I want you guys, maybe if you can see, if you have intentions of taking calculus, you can see where that route goes, where that math goes, and you can understand the importance of it right now so that you kind of dedicate yourself to learning it right now. Does that make sense? Okay. Okay, so that is the actual graph right there. Okay. Now our graph, I would argue, is pretty ugly in comparison to that, right? Okay. However, is this branch right here, this going off to positive infinity for the end behavior. Is that what we modeled right here? Did we have a 0 at 2? Did it have that kind of inverted S shape right there at 2? That's what we showed. Now, essentially, everywhere between like here to there, okay, we are inaccurate. Okay, but did we bump here at 0, 0? Okay, we had tangency there, right? And we came back down. Now, here in this blue, we didn't know how low to go. Okay, but then I bounced back up. I hit that x-intercept at -1, and we were tangent to that, so it went back down. Okay, now as you look at this is why I kind of highlighted the end behavior here. I kind of let that end behavior kind of go progressively. It was a little slow to get down there, right? But we see here, it's kind of a steep slope, right? And those are things that we don't know yet because of our limit in regards to, or our limits in regards to our knowledge about calculus. But to do the calculus, we first need to be able to collect these points, collect these x-intercepts, understand the behavior at these x-intercepts, understand the end behavior. Does that make sense, everybody? And then calculus fills in the gaps. Okay. Let's see. Your homework is going to ask things like this. I'm going to do 3 questions here. We'll say find P of x with the least possible degree that has zeros of 2, 5, 0, and -1.
We already go over what zeros are.
Zeros are, yes, we did. There was a blue box that had 4 statements that said these are all equivalent, and zeros were your x-intercepts. Okay, because it's when we plug in that value, we plug in 2 to our polynomial, it evaluates out to be a y value of 0. I plug in -1 to my x in my polynomial, it evaluates out to be 0. If I plug in 5, plug in 0, the same thing. Okay. Now, if I look at that, if I say I've got those zeros, just a real quick question. What's my y-intercept before we even do anything? 0. How'd you know that? Because one of the x-intercepts is 0. What if I did this? If I made that a 9. Can I ask that question now?
No.
No. You don't know what your y-intercept is now, right? Okay. You could do a little bit of work, which wouldn't be all that hard to figure it out, but it's much easier with that question. Okay. So if those are zeros, and going back to that chart that Blaze was mentioning, got that one, this one right here.
Oh, I wrote that down.
If C is a 0, then x minus C is a factor. That make sense? If C is a 0, x minus C is a factor. So when we're down here, shut up. If these are my C values, then x minus C is a factor. Does that make sense? So when I create my polynomial P of x, okay, it's going to be x minus 2. Okay? Now, when it says of least possible degree, that's telling me what my multiplicities have to be here. Okay? If it's least possible degree, and they're not specifying that 2 has a multiplicity of 2, or has an even multiplicity, or an odd multiplicity, or anything like that, then I'm going to make the assumption that that has to be a multiplicity of 1. Does that make sense? Okay? Least degree, multiplicity of 1 in this case. Now, the next one's going to be x minus 5. The next one is x minus 0. I don't think anybody would write it that way, but we can. And it'd be x plus 1 then, right? Okay. Now, if you FOIL this, and I'll let you do that on your own. I'll just do it real quick here. Expand x times x minus 2, x minus 5, x plus 1. Alright, so this will actually end up being x to the 4th minus 6x cubed plus 3x squared plus 10x. Okay? And that's the polynomial of least degree that has those zeros. Does that make sense? Now I want to show you something real quick. I just FOILed it out. FOIL those two out, multiply by x. Okay, and then whatever that is, distribute the x plus 1 to it. That make sense?
Did we put that in the GeoGebra, or did we just change that negative one?
Yeah, I don't really want you to, I mean, my hope is right now that we can do that though, right? If I restrict you from being able to use GeoGebra for any reason, you can still multiply these, right?
Wait, so we typed the first two.
Yeah, just,
The second two.
yeah, I just took x minus 2 times x minus 5, so it's x
I can do that part.
x squared minus 7x plus 10, right?
I can do that part.
Multiply that by x, give me x to the 3rd minus 7x squared minus 10x,
And then use more fun off.
and then x plus 1.
Okay.
But let's just kind of graph that real quick. We've got x to the 4th minus 6x cubed plus 3x squared plus 10x. Okay. Now they're all odd degree of 1, so that's why we're passing straight through. There's no kind of 3rd degree or 5th degree kind of behavior at these zeros. So that's my graph, right? Okay. Now here's another key point to realize here. If I take, let's see here, I want to find the x-intercepts here. So let's go roots. Say again?
Would we be able to graph it if we just plug in like the not factored version?
What do you mean?
Okay, you know where everything is in parentheses? Like,
Yeah.
if we plug that in with it.
And right here?
Yeah, we do.
Yes, same thing. Yep. If I take A times f of x, where A is a slider, and it's essentially a multiplier out in front of this thing, right? Okay, and right now A is at 1, so we're seeing the red graph and the blue graph on top of one another, right? Would you guys agree that this red graph, though, still has the same zeros? That makes sense? So how many polynomials are there that have these zeros of least degree? Infinite, right? Okay. So what they're going to ask you to do at some point, they might say, we've got the point, let's just kind of make this, hopefully made it easy. 1, 16. Okay. So they'll say, this is kind of what we call a general P of x, okay, because there's an infinite number that go through that. Let's say that we have this polynomial, but we also know that it passes through the point 1, 16. Can I plug in 16 right there? That's my P of x, right? Can I plug in 1 here? Okay, now have this A out in front, and that A is that multiplier, that's that vertical stretch that we're looking for. Does that make sense? And now if I multiply all that out, I should be able to get, I believe this all turns into 8 here. I would get 8A equals 16. Well, what's A going to be then? A equals 2. And then I could put that 2 right there. Or I could multiply it through there. I get 2x to the 4th minus 12x cubed plus 6x squared plus 20x. And that what we call a specific P of x, because we have that additional 116 that has to pass through. They'll give you an extra point that is not a 0. Sometimes it's a y-intercept, but they'll give you an extra point to see if you can find that multiplier. Yes? Yes? Sure? Let's do this one. Let's go find P of x with least degree with zeros of 2 that has a multiplicity of 3, of 1 with a multiplicity of 2, and negative 3 with a multiplicity of multiplicity of 2. All right, so I'm trying to find P of x. And it's got to be least degree. Okay? So they're telling me that I've got a multiplicity of 3 here. So that's going to be x minus 2 cubed, right? Okay. X minus 1 squared. X minus negative 3 squared. And that would be the polynomial of least degree. It would be degree 7. Add my exponents, right? 3, 2, 2. Okay. Now, if we wanted to find a specific one, it might say, okay, it also goes through like 0, 5 or something like that. And you plug in 0 for x's, 5 for your P of x, and then solve for the A out in front.
Wait, so the parentheses are factored?
Say again? Yeah, it's factored.
Okay. Wait, no, okay.
They might, I don't know, it depends on the question. I would argue that they're probably not going to ask you to expand that one, because it's to the 7th degree, and that's kind of nasty. They might ask you to expand like 3rd degrees, 4th degrees, 5th degrees. But anything beyond that, I think they'd probably not require. Okay. The next question that they're going to do.
Yeah, 5 minutes.
I know, I got 2 things to cover with you. Same question. Find P of x of least degree with the following. All right, so I'm going to give you, let's say 1, 2, 3, 4, 5. Let's go out here to 5. Let's have a 0 here. So negative 1, negative 2, negative 3. Let's put a 0 there and a 0 there. Okay, I'm going to show you the graph. And my graph is going to look like that there. It's going to look like that there. And let's say that there. And let's go that there. So I'll kind of fill in the gaps. So that's what my graph looks like. And I'll give you something like that. Now, if you find the P of x of least degree. Now, here's the thing. Look at that far left intercept. It's not degree 1 because it doesn't pass straight through, right? So then it could be 3rd degree, 5th degree, 7th degree, 9th degree, 11th degree, whatever, right? Could be 101st degree. But if my polynomial is going to be of least degree, can that thing be to the 101st power?
Probably not.
No, it has to be to what power? It has to be the third power. Okay? So that's a multiplicity of 3. What about this one? It could be squared to the 4th, to the 6th, to the 8th. If it's multiplicity of least degree, or p of x of least degree, that has to be multiplicity 2. What about that one? Passes straight through. That's 1. Okay? And the last one has got to be a multiplicity of 3. There we go. So that's 1. And this one's multiplicity of 3. So, okay. Let's find our p of x then. That's a minus 3, right? So it'd be x plus 3 cubed. This would be x plus 1 squared. This would be x minus 2. This would be x minus 5 cubed. So p of x is going to be 3, 5, 6. Be x to the 9th eventually, right? That'd be the leading degree. Does x to the 9th have that in behavior?
Yes.
Yeah. Okay. So now understand that if I make that x plus 3 to the 5th, x plus 1 to the 4th, x minus 2 to the 1st, x minus 5 to, let's say, the 7th, the graph is going to look very similar. The y values are going to change drastically, but the intercepts and the behaviors at those intercepts will be very similar to what we see right there. Okay? So that's why I say least degree, to get that one specific that everybody has the same answer to. Okay? How many maximums and minimums does this thing have? There's 1, right? There's 2, 3, 4. Is 4 less than that number right there? Okay. What? Okay, good. So if I had, like, I'll just say x to the 5th here. We talked earlier that if it's x to the 5th, how many zeros could it have? Could it have 5 zeros? If there's no redundancy, 5 separate zeros. Well, x to the 5th does have the end behavior of that and that, doesn't it? Okay, well, if these are singular multiplicities, then we need to pass through them, right? If I pass through that one, then I got to bend to pass through that one, right? I got to turn. And then here I got to turn again, right? Turn again. Turn again, right? You got 1, 2, 3, 4 turning points, right? How does that relate to that number right there? 1 less, right? Can I have 5? Can I have 5 turning points if it's 5th degree? No, because it's going to turn, and it would have to have another 0, and it would ruin the end behavior, right? Okay? So what we learned, now it could have less. It could have only 3. Could have maybe only 1. Does that make sense? Could have 0, an x to the 5th. If I graph x to the 5th, just x to the 5th, it's going to look like that, right? There are 0 maximum minimums there. Local maximums, local minimums. Okay? So what we have here is a rule that says, you don't need to write this down. It says if p of x, you don't need to write that down, is a polynomial of degree n, then the graph of p has at most n minus 1 local extrema. Yep. Which basically, you'll see, I think in websites sometimes called them turning points. Okay? You only have n minus 1. At most. You can have n minus 2, n minus 3, but n minus 1 is the most you can have. Finish that homework. Let's do it tomorrow night.
Are you going to extend my homework?
Woo!
Are you going to extend my homework?
No, it says it's on the...
What homework that says going to extend?
The one that ended up being...
The one that Sarah asked me about, and you said, yeah, I did that too, but you never came and asked me to change it?
Yeah.
Yeah.
I requested it on the website.
Oh, I don't read those.
Website.
That's easy to request those. Is it easy to do that, or is it hard, or is it easy to have the conversation with me right now? Which one's harder? Having the conversation, right? Don't make you have a conversation. Yes, talk to
The thing said November 6th on the website.
It does. What's today?
The 4th.
Okay, I'll leave it open to the 6th then. I got bad breath, Chuck?
Well, you're like an inch away from it. Yeah.
I'll feel brush my teeth back.
Yeah, that's what it said.
Shut up. Huh?
I have an appointment.
Sign out, please. Yes.
I go get a pen and paper?
Yeah,